Welcome to the Deep Dive, where we take stacks of information and distill them into the key insights, just for you. Today, we're tackling something, well, pretty common. How do you know if that marketing campaign really worked? Or if one medical treatment is genuinely better than another? When the data is always a bit messy, how do we cut through that noise, that variability, to actually make confident decisions based on data? So our mission in this deep dive is to explore one really powerful but surprisingly accessible tool for doing just that. It's called the T-test. We'll dig into what it is, where it's used, and some practical tips for actually using it yourself. Hopefully it'll help you sharpen your own data analysis skills. And we're really leaning on Dr. Chinmoy Pal's excellent work here, especially his piece, the T-test, Unlocking Data Insights. Okay, let's unpack this right away. What exactly is a T-test at its core?
Right. So at its heart, the t-test is a statistical method. It's basically designed to tell you if there's a significant difference between the averages, the means of two groups. Think of it as a way to check if the average results you're seeing from two different sets of data are truly distinct, or if maybe, just maybe, the difference you see is down to random chance, sampling variation.
Okay. So it's about getting past the maybe and getting to a more solid conclusion.
Exactly. It helps you draw more robust conclusions from your data.
That sounds incredibly useful. It really gets to the heart of so many real-world questions. Where did it come from? Who developed it? What problem were they trying to solve?
Yeah, it's got a great origin story, actually. It was developed back in the early 20th century by a statistician named William Seeley Gossett. And interestingly, he worked for Guinness Brewery.
Guinness, the beer.
Yeah.
Seriously.
Yep. He needed a reliable way to check the quality of batches of stout, specifically when he only had small samples to work with. And critically, this was often when he didn't know the true variability of the whole population of stout they were doing.
So practical problem solving right there.
Totally. And because Guinness didn't want their competitors knowing about their methods, trade secrets, and all that he had to publish his work under a pseudonym, he used student.
So that's why you sometimes hear it called student's T-test.
That's the one. And it took off. It became indispensable pretty quickly in fields way beyond brewing psychology, biology, economics, you name it. And its real strength is precisely what Gossett needed it for. It works really well with those small sample sizes, and when you don't know the population's standard deviation, which, let's be honest, is often the situation you find yourself in with real-world data.
That's fascinating. The brewery connection makes it so much more relatable. Okay, so it's versatile, good for small samples. But is it just one test? Or are there different flavors of T-test for different situations?
Oh, absolutely. It's not a one-size-fits-all tool. There are variations, yeah. We generally talk about three main types, and each one is tailored for a specific kind of comparison scenario.
Okay, what are they?
So first up, you've got the independent samples t-test. This is probably the most common one you'll see. You use this when you're comparing the means of two completely separate independent groups. Think testing a new drug on one group of patients versus a placebo on a different group of patients. Their outcomes aren't related.
Okay, two separate groups. Makes sense. What's next?
Then there's the paired samples t-test. This one's different because you use it when you're comparing means from the same group, but at different points in time or maybe under different conditions. The classic example here is measuring something before and after an intervention, like testing students' knowledge before a course and then again after the course. The before and after scores are paired for each student.
Right, so you're comparing individuals against themselves in a way.
Exactly. And the third main type is the one-sample t-test. This one you use when you have just a single group and you want to see if its mean is significantly different from some known value or maybe a theoretical expectation or a target.
Like comparing the average height of students in one specific school to the known national average height.
Precisely. Or checking if the output of a manufacturing process meets a specific quality standard.
Okay, that breakdown is really helpful. Independent groups, paired measurements, or one group against a benchmark. Now, here's where it gets really interesting for me. Let's talk about putting this into action. Can you give us some more concrete, real-world examples? Where does this T-test really shine across different fields?
Definitely. It pops up everywhere, honestly. In medical research, as we touched on, it's fundamental for comparing treatment effectiveness. New drug versus placebo, or maybe comparing two different surgical techniques. It helps decide which is better.
Crucial decisions there.
Absolutely. Then in education, researchers might use it to see if, say, a new teaching method leads to significantly higher test scores compared to the traditional method. You'd use an independent samples test for that, comparing the two groups of students. In the business world, maybe in marketing or web analytics, you could use it to assess if changing the layout of a web page significantly increased the time users spent on the site. Or maybe comparing sales figures between two different regions. Is region A genuinely outperforming region B, or is it just random fluctuation?
So helping businesses make smarter decisions about strategy or design.
Exactly. And in psychology, it's used all the time. For instance, investigating if a therapy intervention significantly reduces anxiety scores compared to a control group, or maybe comparing reaction times under two different stimuli.
It sounds like the common thread here is its ability to give you a number, a quantitative measure of whether a difference you're seeing is likely real or just, random noise.
That's the core value, yes. It provides that assessment of statistical significance. It helps you sort out whether observed differences are likely due to a genuine effect, the drug working, the teaching method being better, or just due to chance. And that makes it vital for both experiments where you actively change something and observational studies where you're just comparing existing groups.
Right, but you mentioned statistical significance. Is there a catch? Does statistically significant always mean important?
That's a really critical point and a common misunderstanding. No, statistical significance doesn't automatically equal practical importance or magnitude. A t-test might give you a very small p-value telling you the difference is unlikely to be chance, but the actual size of that difference might be tiny, maybe too small to matter in the real world.
Okay, so a statistically significant result could still be practically meaningless depending on the context. Good distinction.
Definitely something to keep in mind when you interpret results.
So let's say someone listening is thinking, okay, I have some data, I think a t-test might be right. How do they actually do it? What are the practical steps involved? Walk us through it.
Okay, yeah. There's a pretty standard workflow, usually about 6 key steps. Step 1, and this is arguably the most critical, is to formulate your hypotheses. Before you even touch the data, you need to be clear about what you're testing. You define your null hypothesis, usually written as H0, H-or. This typically states there's no difference or no effect. It's the status quo, the thing you're trying to disprove.
Like the new drug has no effect.
Exactly. Then you define your alternative hypothesis, H1, HR. This is what you suspect might be true, that there is a significant difference, like the new drug does improve outcomes. Getting these clear upfront is crucial. A common pitfall is being vague here, which makes interpreting the end result really hard.
Okay, state your claim and the opposite clearly. Got it. What's step 2?
Step 2 is super important. Check your assumptions. The t-test isn't magic. It relies on your data meeting certain conditions to be valid.
The fine print. What are the main assumptions?
There are generally 3 big ones. First, normality. The data within each group you're comparing should be roughly normally distributed, bell-shaped. It doesn't have to be perfect, especially with larger samples, but major skewness is a problem. Second, homogeneity of variance. This means the spread or variance of the data should be similar in the 2 groups you're comparing. There are tests for this, like Levine's test.
So one group shouldn't be way more spread out than the other.
Ideally, yes. If they're wildly different, it can affect the result. And third, independence. Each observation, each data point should be independent. One person's score shouldn't influence another's. This is usually about study design. Random sampling helps here.
And if you skip these checks?
Big risk. Your t-test results could be misleading, basically invalid. You might think you found something significant when you haven't, or vice versa. It's like building a house on shaky ground.
Okay, check assumptions carefully. What's step 3?
Step 3 is to choose the appropriate t-test. Based on your hypotheses and how your data is structured, remember our discussion about independent groups, paired data, or one sample against a standard. You pick the specific type of t-test that fits.
Right, use the right tool for the job. Independent, paired, or one sample.
Exactly. Using the wrong one will mess up your analysis. Then, step 4 is where the number crunching happens. Calculate the t-statistic. This involves a formula, but basically it measures the difference between your group means relative to the variability or spread within your groups. It boils down to difference between means, standard error of the difference.
Standard error, that's like how much the sample mean is likely to vary.
Yeah, it's a measure of the precision of your sample mean. You get a single number, the t-statistic, from this calculation. Most people use statistical software, SPSS, R, Python, Excel, even to do this step.
Okay, so the software spits out a t-value. What do you do with it? Step 5?
Step 5 is interpret the results. This is where you figure out what that t-statistic means. You compare your calculated t-value to a critical value from the t-distribution. This critical value depends on your chosen significance level, often called alpha, usually set at 0.05, and something called degrees of freedom, which is related to your sample size.
Degrees of freedom. Sounds technical.
It is a bit, but essentially it reflects how much information went into estimating the variance. Software calculates it for you. More commonly nowadays, though, you look at the p-value that the software gives you alongside the t-statistic.
Ah, the famous p-value.
Yep. If the p-value is less than your chosen significance level, like less than 0.05, you conclude that your result is statistically significant and you reject the null hypothesis.
So a p-value below 0.05 means it's unlikely I'd see a difference this big if there is really no effect.
That's the logic, precisely. It suggests the difference you observed is probably real, not just random chance.
Okay, so you've run the test, checked the p-value, made your decision about the hypothesis. What's the final step?
Step 6 is to report your findings. You need to communicate what you found clearly and concisely. This usually means reporting the type of t-test used, the calculated t-statistic, the degrees of freedom, often written as DF, and critically, the p-value. Sometimes you'll also include confidence intervals for the difference between means, which gives a sense of the plausible range for the true effect size.
So just giving the p-value isn't enough.
Best practice is to provide the context. The t-value and degrees of freedom tell people more about the test itself. Clarity is key so others can understand and evaluate your work.
That's a fantastic roadmap. Formulate hypotheses, check assumptions, choose the test, calculate the statistic, interpret the p-value, and report clearly. Let's try and bring that all together. You mentioned pharmaceutical companies earlier. Could we walk through that drug trial example using these 6 steps, make it really concrete?
Sure, perfect example. Let's imagine this company, PharmaCore, has a new drug they think improves patient recovery scores. They run a double-blind study. Step 1, hypotheses, null, H. The drug has no effect on recovery scores, mean difference equals 0. Alternative, HO. The drug improves recovery scores, mean score for drug group, mean score for placebo group.
Okay, clear goal.
Step 2, assumptions. They'd collect the recovery score data from both the drug group and the placebo group, then they'd check. Are the scores in each group roughly normally distributed? Are the variances similar between the groups? Are the patient's results independent? Let's assume for this example, yes, the assumptions hold.
Good to go on the data front.
Step 3, choose test. They have 2 separate independent groups, drug versus placebo. So an independent samples t-test is the right choice.
Makes sense.
Step 4, calculate. They feed the recovery scores into their statistical software. Let's say the software calculates that the average improvement score for the drug group was 5.2, and for the placebo group, it was 3.1. The software crunches the numbers and gives them a t-statistic. Maybe it comes out as t equals 2.45.
Okay, t equals 2.45. Now the interpretation.
Step 5, interpret. The software also gives them a p-value associated with that t-statistic and the degrees of freedom, which depends on the number of patients. Let's say the p-value is 0.03.
0.03, that's less than 0.05.
Exactly. Since 0.03 is less than the standard alpha level of 0.05, they conclude the result is statistically significant. They reject the null hypothesis. The evidence suggests the drug does have an effect.
So the difference between 5.2 and 3.1 isn't just random noise.
According to the test, it's unlikely to be just random noise. There's only a 3% chance they'd see a difference that large or larger if the drug truly had 0 effect. Step 6, report. PharmaCore would write up the findings, maybe stating something like, an independent samples t-test showed that the new drug led to significantly higher patient recovery scores, mean equals 5.2, compared to placebo, mean equals 3.1, TDS equals 2.45, p equals 0.03. They'd fill in the actual degrees of freedom for DF.
Wow, okay, seeing it step by step like that makes it really clear. So what does this all mean for PharmaCore in this scenario?
Well, it gives them a strong data-driven reason to be confident about their drug. That t-test result provides quantitative evidence that the improvement seen wasn't just a fluke. It supports moving forward, maybe towards getting approval or further testing.
It transforms an observation, hey, the drug group seemed to do better, into a statistically backed conclusion.
Precisely. Without the t-test, that 2.1 unit difference is just a difference. The t-test gives it statistical weight, helping them distinguish a real signal from the background noise.
That really hammers home the core takeaway for today, I think.
Yeah.
The t-test, in its various forms, is just a fundamentally powerful tool for understanding if differences between groups are meaningful. It helps us make sense of data in a structured way.
Absolutely. And really understanding how it works, its different types, those assumptions, and the steps to actually use it that can significantly boost your analytical skills. Whether you're doing academic research, working in industry, analyzing survey results, it's a cornerstone technique.
It feels like a key step towards making genuinely data-informed decisions, rather than just going on gut feeling.
Definitely. It adds rigor to your comparisons.
So as we wrap up, let's leave you, the listener, with a few thoughts to mull over, building on everything we've discussed. First, thinking about that crucial difference between statistical significance and practical importance, how might the results of a t-test influence decision-making in your specific field? And how would you ensure you're considering both types of significance? Second, reflecting on those assumptions. Normality, equal variances, independence. In what ways can a deeper understanding of these prevent common statistical errors in your own work or analysis? What might you do if your data doesn't quite meet them? And finally, a forward-looking one. If a t-test helps confirm a significant difference between two groups, what might be the next question you'd ask? What further analysis could help you understand that difference more deeply? Some things to chew on there. We really encourage you to reflect on those questions to deepen your own understanding of the t-test, how it can empower your data analysis.